about modeling and simulation for the space industry. We are LEAP Australia. We are proposing and providing workflows in modeling and simulation. And we would like to talk a little bit today about what is possible, what can be seen for especially the space industry. So this is how the range of applications and industries looked in 2005. Pretty much mining, trailers, trucks, a little bit of railway. This was a slide actually from our set that showed what we can do from our consulting support. Of course, that has changed, and simulation is evolving as well a lot. One example is, for example, digital twins. That came up around 2010, for example. So this is not exactly a digital twin, but it is actually a good representation of an overall system simulation, where you have an insulin pump. It's modeling the electrical system. You get even the user interface, you get the embedded software that is making the decision, and you even including 3D modeling for fluid flow simulation to look what the doses is for the patient correctly. So everything in one model, everything ready to go and really good to test certain applications. Another big topic was additive manufacturing, and I think that is a very, very relevant for space as well. Keeping stiffness and also reducing weight is very relevant and important. And we have a full workflow for that. So you do the topology optimization, you validate your design, and in the end you simulate the process of your 3D printing in the machine later on, down to a microstructure analysis. And this is a small last example with the big revolution in autonomous. This is for traffic. So what the key is here is that it's a platform that connects the physical sensor. In this case, it's a LiDAR, but it could also be a camera. It could also be a radar system connected to the decision-making software, embedded into a traffic environment that allows you to model different scenarios, different weather conditions, and then you can see and you can detect where are problems coming up, where's issues. And you can also use that to teach and have the algorithm learning from the camera picture, the sensor picture, and so on, inside the scenarios in the traffic. So what can be done for space? And there are many, many things that we are doing for many, many years already. For example, antenna placement is a big topic for all the industries. Then charge is a big topic. But also the classical ones, thermal and structural integrity. We're looking at spacecrafts and satellites. And then also the topic of multipaction, which is really, really niche. We're trying to avoid breakdowns in, for example, microwave equipment, like, for example, cavities and waveguides. One quick example, of course, antennas. And I know in the audience there are people who are knowing much more about antennas than I do. Just as a helic antenna, designing one, and then you deploy that as an array on a ground plane. Very important if you want to get radiation patterns out, and people are also interested in the link between those different single antennas. But what's really important is that you need to simulate the platform as well, because that changes the antenna performance. And you can see that in that picture. If I place another part in the vicinity, like a dish antenna, you can see that there are side lobe levels going up on the right side. So super important to have your antenna designed in free space, but then moving on the platform and simulating it as well. One benefit of simulation, of course, you can look at the fields and visualize the fields so you can see what's going on and how your device actually functions. So then we had a look and asked ourselves, where are the mission failures coming from? Where are that are coming from problems in the design? And looking through different literatures and trying to connect what we can do and how we can help, is that mainly reliability problems in electronics and charge problems are a big topic for mission failures, taking away the infant mortality and taking also away launch problems, of course, but looking at very, very long term operations. And what you really need to do when you look at the reliability of electronics is to stack up the life cycle of a device, it can be an electronics unit, across different events. So you can start with manufacturing, you can also use the transport, but what's for us important is, of course, the launch is a very, very important event in its life cycle. And we can model that launch by just directly putting a PSD in after you have done your design from Altium, and then creating a life curve. So in that case, we're using the probability that you have to put in, probability of failure that you can live with, that you are okay with, and of course the life cycle. So you're intending to have your device operating in space for more than 5 years or 5 years. So we create that box, and then we can calculate when is it failing. And we can do that actually in a second event for the shock analysis as well, when the equipment separates from the rocket, and we do the same. So in the next step, we are in orbit. And what's problematic in orbit is the temperature changes. So what we do is we look at the temperature in the electronics, try to understand when is the electronics operating and when is it not operating, because not all the electronics are operating all the time. So the temperatures are slightly different. And we also assume or take temperatures from that the satellite sees in space. And from that we are creating a profile. Just a profile over time that is that event, and we can then run it over 500 cycles or whatever it is what we have across the 5 years in space. We can also use it from SDK, so if you have a concrete mission data where you want to, for example, get your temperature fluxes for a concrete mission, for a flight path of your satellite, you can also get that from SDK. So then we can create a life curve for that as well, and you can see with the solar fatigue, the board is failing after 2.5 years and is not reaching the 5 years. Understanding then what goes wrong is very important, and of course you can do countermeasures, you can do redesigns and all those things. We can drill down to each component and show you which component and what component is causing the problem, which one is failing first. And we can also change solder material very, very quickly and rerun the analysis. So in the end, and that's the biggest benefit of that workflow, is the tool and the software and the workflow stacks up all those events with all their failure rates and creates an overall combined failure rate across those events. So you get a feedback, am I safe in my mission for the electronics unit or not? Let's stay in orbit, and this is my last half of the presentation. The biggest problem there is charging, and just in a nutshell, particles are hitting the structure, there is electric fields created inside, they're penetrating low conductive materials, and with that you get arcing, and the arcing can cause problems on the communication equipment, but the arcing also can cause breakdown and damage in the material. And we have a partner in the US who has created a facility where you can test that. So it's a vacuum chamber that mimics the temperatures, and it allows you to bombard your device with different particles, differently charged in different amounts, very, very flexible for whatever orbit you would like to look at. It's got an antenna inside, you can see that, so to pick up EMI and radiation from those events. And it's also got a camera, so you can actually see the discharge. The same company has created a technology which allows to simulate that chamber. So we have a tool that can do that for you. So if you have a CAD model or a device, and you can put that in and then get different energy levels and a mix of energy levels and bombard your structure virtually. This is an example on a solar cell that we have done. The setup is very simple. Electric potentials on each plate if you want to mimic the operation. And then you have the electrons, the incident electrons for a different or for a given orbit. And then you can test that, and the results are looking like that. So you can, over time, look at the bombardment and you can see where the discharge is happening. And you could also look at charge densities, and you could look at electric fields. So a very good way of pre-complying, pre-testing before going into a chamber and before going to testing. And that's the main message we want to give. Lower your costs by simulating first and then having the confidence going into the full test. If you want flux levels for a mission or for a mission specific, you can do that as well. Again, my colleague Bennett is here at our booth. He can model those things in SDK and get those data out of SDK and put it then into our virtual vacuum chamber. So that's basically it. A couple of ideas and workflows, what can be done to take risks out and test things specific for space environments. If there are questions, we would be happy to answer them.